Hello again, everyone. Welcome back to Statistics. Today we're in our final section. We're going to talk about section 10.3, Hypothesis Tests for a Population Mean. So today I'll show you how to do that hypothesis test about a mean, and we also will talk for just a minute about how to understand the difference between statistical significance and practical significance. So let's go ahead and get started. Now, before I just load you down with a bunch of rules and formulas, I want to make sure you understand exactly what it is that hypothesis testing is supposed to be doing for us. So let me take you through a little situation that will be, I think, easy to visualize. So imagine that your college algebra instructor has announced that 2,000 students took the midterm this semester, and the population mean exam score on the midterm was 85. And let's suppose that you're a little skeptical of that instructor's claim. So you poll a random sample of 50 students, and you find that the mean of your sample is 83. So my question is, does that sample mean lead you to believe that the instructor was wrong? Now remember, we only polled a sample of 50, so it's not reasonable to expect that our sample mean will be 85 exactly. It could be a little different, but how much difference can we tolerate? Well, let's suppose that you do a little calculating, and you find that the probability of obtaining a sample mean of 83 from a population whose mean is 85, that probability is 0.25, in other words, 25%. Well, that's a pretty high probability. That would not be an unusual event at all. So I think in this case, we would say that the likelihood of obtaining this type of sample from this type of population is a relatively high probability. And so we would conclude that although our sample mean was a little less, there's not enough difference between our sample mean and the instructor's claimed population mean to prove that the instructor is wrong. On the other hand, suppose we poll 50 students and we find that the sample mean is 60, and you do your calculations again and you find that the probability of obtaining a sample mean of 60 from a population whose mean is 85, that probability is only 2%. And so now we know that anything with a probability of less than 5% is considered an unusual event. So there are two possibilities. Either 85 is the correct population mean and we just happen to collect a very unusual sample because, it's only a 2% chance, but it could happen. Or there's actually nothing unusual about our sample. It just happens to come from a population whose mean is less than 85. In other words, the instructor's claim is incorrect. So in this case, because the probability of obtaining a sample mean of 60 from a population whose mean is 85 is so small, we would probably conclude that it's more likely that the instructor's statement is wrong and that the population mean is not actually 85. So here's my question. What's the cutoff? When the probability of obtaining our particular sample mean was 25%, we were perfectly happy to say, well, that could happen, no big deal. But when the probability of obtaining our sample mean was 2%, then we were like, oh, wait a minute, I'm not sure that I believe that could happen by chance. So somewhere between 2% and 25%, there was a line that we crossed. And so the question is, how small does that probability need to be before we decide that the null hypothesis is wrong? Well, the process of hypothesis testing helps us turn these gut feelings into numbers that we can analyze. So that probability would be different for different situations, and hypothesis testing helps us find out what that number ought to be. So in hypothesis testing, the main idea is to compare the probability of obtaining the sample mean by chance to the level of significance, which is alpha, which is the smallest probability that we're willing to attribute to chance. If the probability of obtaining the sample mean by chance is less than the level of significance, then we take that as evidence that the null hypothesis is wrong. Just like on the last slide, when we obtained a sample mean of 60, the probability of that was so small, it was smaller than our level of significance, so we took that as evidence that the instructor's claim was wrong. It's just that up till now, we haven't been able to put a number on this level of significance. So hypothesis testing is going to help us compare the probability of obtaining our sample mean by chance to this level of significance. Now this comparison can be made in two ways. The first way I'm going to show you is called the classical approach, where we are going to compare the t-score of our sample mean, which is called the test statistic, to the t-score of the level of significance, which is called the critical value. So in classical approach, we're comparing t-score to t-score. We'll be comparing the test statistic, which comes from the sample, to the critical value, which comes from the level of significance. And then there's the p-value approach, where we will compare the probability of obtaining our sample mean, which is called a p-value, to the level of significance, which we know as alpha. Now, I need to show you both ways because the classical approach is easier to understand the first time you're going through it, but p-value is easier to use with technology. So we're going to do both kinds of problems, but remember that if you ever have to look at any scientific research that uses hypothesis testing, like drug trials or things like that, that you'll almost always see p-values used. So the classical method is good for understanding, but p-value is what people really use because that's the easiest thing to get from a computer. Now, just like we saw with confidence intervals, there are certain criteria that have to be met before we can perform the hypothesis test. So, before we can conduct a hypothesis test, we have to know that the sample was obtained using simple random sampling, or it came from a randomized experiment. We have to know that the sample has no outliers, because if the sample has outliers, that's going to affect the sample mean and the sample standard deviation, because neither one of those is resistant, so that would throw everything off. We also need to know that the population from which the sample is drawn is normally distributed, or the sample size n is large. And remember, what we mean by large is that n is at least 30. And then finally, we have to know that the sampled values are independent of each other. So I think these are pretty much the same requirements that we had on confidence intervals. The sample has to be obtained using simple random sampling. The sample can't contain any outliers. The population from which the sample is drawn either needs to be normally distributed, or we have to have a large sample. Remember, the central limit theorem covers us here as long as n is greater than or equal to 30. And then the sampled values need to be independent. So now I'm going to give you the steps for conducting a hypothesis test about a mean using the classical approach. Step 1 is to determine the null and alternative hypotheses. We already looked at how to do that back in section 10.1. Step 2 is to select a level of significance, which we call alpha, and we do that depending on the seriousness of making a type 1 error. So if the consequences of making a type 1 error are really bad, like it's going to put someone's life or even health at stake, then we would want to minimize the probability of a type 1 error, and we would want alpha to be very small. Now, in all the problems we're going to be assigned from our book, they're going to give us a level of significance, but in real life, nobody just tells you the level of significance. You would have to choose it yourself. And then step 3 is to compute the test statistic. Now this t sub 0, that's called the test statistic, and look at this formula. This formula should be pretty familiar to us. We have already been calculating t-scores, and so I know you've seen this formula before. Now x bar, of course, is the sample mean. Mu sub 0 is the number in our hypothesis. Of course, S is the sample standard deviation, and of course, N is sample size. So after we compute the test statistic, then we will use the t-table to determine the critical value based on alpha. In other words, alpha is the area in the tails of the standard normal curve, and then the critical value is the t-score that matches that area. and then we draw a normal curve and we put our critical value on that normal curve, and we shade the appropriate tail either right or left or both. And then in step 4, we compare the test statistic to the critical value. If the test statistic falls in the shaded region, we reject the null hypothesis. If it doesn't, then we don't reject the null hypothesis. Now that we have the steps, let's do a few examples together so you can see how the process works. I'm going to read this problem with you. This says the mean height of American males is 69.5 inches. The heights of the 43 male U.S. presidents, Washington through Obama, have a mean of 70.78 inches and a standard deviation of 2.77 inches. Treating the 43 presidents as a simple random sample, determine if there is evidence to suggest that U.S. presidents are taller than the average American male. Use the alpha equals 0.05 level of significance. Now, if you're thinking like I was that, hey, wait a minute, Obama was the 44th president, remember Grover Cleveland was elected twice to 2 non-consecutive terms. So when we're numbering the presidents, he counts twice, and that's how we get President Obama as number 44. But when we are trying to list all the heights, he only counts once because he's only one person. So that's how we got 43 here, even though technically Obama was the 44th president. Now, in hypothesis testing, remember the first thing to do is to write your hypothesis pair. So I'm going to go ahead and label a null hypothesis and an alternative hypothesis. Remember, the null hypothesis is the hypothesis of no change, or the hypothesis of equality. So the null hypothesis would be that mu equals 69.5. And remember that the alternative hypothesis is always a statement of inequality. So we're trying to find evidence to suggest that U.S. presidents are taller than the average American male. So our alternative hypothesis would be that mu is greater than 69.5. And that's step 1 of the hypothesis testing procedure. Step 2, remember, is to find the level of significance. So they've given us that. The level of significance is 0.05. Now, step 3 is to compute the test statistic and then find the critical value and then draw the normal curve and shade the area beyond the critical value. So first, let's find the test statistic. Here is our formula. So our test statistic will be x bar, which is 70.78, minus mu sub 0, which is 69.5, divided by s, which is 2.77, over the square root of n, which is 43. So now you'll put this in your calculator. Remember, after you do the subtraction, you need to press enter and then divide by this quantity and make sure and put this in parentheses. And you should find a test statistic of 3.030. Now just put that on ice for just a second and let's find our critical value. So for the critical value, we know that this is a right-tailed test. I'm going to go ahead and shade the right end. This area represents the level of significance. So this area is 0.05. And now the critical number which we need to find is this t-score that marks off this area of alpha. So you would go to your t-table, and I'm not going to put it up on the screen here, but I hope you've got your t-table in front of you. And we need to know now the degrees of freedom. Remember, n is 43, and that means degrees of freedom is 42. But when you look at the table, you'll find that our t-table goes from degrees of freedom equals 40 to degrees of freedom equals 50. So you just choose the degrees of freedom that's closest to the one you want. So I'll be looking at the 40 line, and you go out to the column for 0.05, and we find that the critical value, which I'll call here T sub crit, so we remember that it's a critical value, T sub crit is 1.684. So that's using degrees of freedom equals 40, and I'm going to label that on my diagram here. So now I know that alpha is 0.05, and that's this area, and the critical value is 1.684. And now we need to compare our test statistic to this critical value. So you just draw the test statistic on your diagram. If the test statistic is in the shaded region, that's called the rejection region, and that means we're going to reject H0. And if the test statistic had fallen here in the unshaded region, we would not reject H0. So we're going to conclude here that we need to reject H0. And if we reject H0, remember that's because our sample provided evidence against H0. So now we're going to say that there is sufficient evidence to conclude that the mean height of U.S. presidents is greater than 69.5. So again, just as a reminder from the last section, when we reject H0, we start our statement by saying there is sufficient evidence to conclude that, and then what comes next is basically H1. So H1 says that the mean is greater than 69.5, and so that's what my statement says here. There is sufficient evidence to conclude that the mean height of U.S. presidents is greater than 69.5. And that is the classical method. Now we're going to go through this procedure a couple more times, and then I will show you the p-value approach. Now our next example deals with a small sample. Remember, the hypothesis testing procedure requires that the population be somewhat normally distributed, or that the sample be at least 30. If you have a sample smaller than 30, then you have to know somehow that the population is somewhat normally distributed, otherwise the test is not valid. Also, if the test contains outliers, this procedure shouldn't be used. So with small samples, we need to look at a box plot and a normal probability plot to make sure that both of these conditions are met. So now here is our next example. This is an exercise from the homework. This says the mean waiting time at the drive-thru of a fast food restaurant from the time an order is placed to the time the order is received is 84.3 seconds. A manager devises a new drive-thru system that he believes will decrease wait time. He initiates the new system at his restaurant and measures the wait time for 10 randomly selected orders. The wait times are provided in the table. So here they are. Now, because this sample is so small, we need some guarantee that it's reasonable to assume that the population that these times came from is normally distributed. And we also need to know that this sample itself contains no outliers. So the textbook has already created for us the normal probability plot and the box plot. You can look at the box plot here and see that there are no outliers. Remember, outliers are denoted by an asterisk beyond the whisker. And you can look at the normal probability plot and see that since these dots are in a relatively straight line, it's reasonable to assume that the population these came from is normally distributed. So having met both of these conditions, we can go ahead with our test. Okay, so I've recopied the data here for us. Now you know that when we get ready to calculate our test statistic, the first thing we're going to need is the X bar and the S from this sample. So the easiest way to get those is to enter these 10 numbers into your calculator and use one variable stats to get them. And now remember that in a show work situation, since this is a hypothesis test problem, really the work we need to see is what relates to the hypothesis test, and we assume that you're going to use the calculator to get the X bar and the S. I have used one variable stats to find that X bar is 78.00 and S is 15.21. And we know that sample size is 10, and therefore we know that degrees of freedom is 9. Now, just a note about rounding. We said earlier that it is a rule of thumb that however many decimal places your data has, your statistics should have one more decimal place. And here it's pretty important that you actually follow that rule, because if you don't, it can generate rounding errors in your test statistic, and it can throw things off for you. So please do be a little careful about your rounding here. Now let's go ahead with our hypothesis pair. We have labels for H0 and H1, And remember, H naught is the hypothesis of equality. So since our restaurant manager is interested in seeing if his new system can beat this time, then H naught should be that mu equals that time still, and H1 should be that mu is less than that time. Now step 2 is to find the level of significance, and they have given that to us here. We know that alpha is 0.1. And now step 3 is to calculate the test statistic, find the critical value using the table, and then draw a normal curve and shade the area represented by alpha. So we'll do that here. We'll say that our test statistic is x bar minus mu, so 78 minus 84.3, divided by 15.21 over square root of 10. And that gives us a test statistic of negative 1.310. Now remember, this is a left-tailed test, so when we draw our normal curve, we will shade the left end, and remember the area in the tail represents alpha. So our alpha is 0.10, and now we need to find the critical value that goes with this area. So notice that this critical value will be negative because it's on the left side of the normal curve. So now you're going to go to your table using degrees of freedom equals 9 and using area in the tail equals 0.1, you will find that the critical value is negative 1.383. Now again, I know the table gives you a positive t-score, but all of the t-scores in the table are positive. You have to be able to look at this diagram and know that this critical value is supposed to be negative because it's on the left side. So the critical value is negative 1.383. And let's just go ahead and label that critical value. And now it's time to draw our test statistic onto our diagram here. And our test statistic is negative 1.310. So that's going to be a little bit to the right of this critical value because it's just a little bit larger than the critical value. And so now you can see that our test statistic is not in the shaded region, and that means we do not reject H naught. And now we can state our conclusion, which would be that there is not enough evidence to conclude that the average drive-through time has dropped below 84.3. You see, his sample mean is less than 84.3, but it's not enough less to prove that the new population mean is less than 84.3. You see, the probability of obtaining a sample mean of 78 from a population whose mean is 84.3 is still large enough that we would assume that this sample happened by chance, and we would not assume that the population mean we already had has changed. Now here is one last example that we will do together by the classical method. This one says the fun size of a Snickers bar is supposed to weigh 20 grams. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so the mean weight is 20.1 grams. The quality control engineer at M&M Mars, the Snickers manufacturer, is concerned about the calibration. He obtains a random sample of 11 candy bars, weighs them, and obtains the data in Table 1. Should the machine be shut down and calibrated? Because shutting down the plant is very expensive, he decides to conduct the test at the alpha equals 0.01 level of significance. So he really wants to minimize the probability of a type 1 error. That is, he wants to be very sure that he's supposed to reject H naught because he does not want to run the risk of rejecting H naught when H naught is actually true. Now, because his sample is so small, he needs to make sure that it's reasonable to assume that the population is normally distributed, and he also needs to make sure that his sample contains no outliers. So we can see from the box plot that the sample contains no outliers. That's good. And we also can see from the normal probability plot that although it does dip down pretty badly here, the dots are actually straight enough for us to go ahead. Remember, the t-distribution is robust, which means it can handle small departures from normality. So we have no outliers in our sample, and this normal probability plot shows that the population is most likely somewhat normally distributed. So it's okay for us to go ahead with our t-test. Now we know that the first thing we're going to need to do is write our null and alternative hypotheses, but we also know that when we get ready to calculate the test statistic, we will need the mean and the standard deviation of this sample. So let's go ahead and put these 11 numbers in our calculators, and we will run the one variable stats command, and we will find that x bar equals 20.301 and s equals 0.640. Notice that I've kept 3 decimal places because my data has 2 decimal places. Also note that n equals 11 and therefore degrees of freedom equals 10. Now I'm going to go ahead with my hypothesis pair. So I have labels for the null hypothesis and the alternative hypothesis. Remember that the engineer is trying to find evidence that the population mean is different from 20.1. So the null hypothesis needs to be that mu equals 20.1, and since the engineer would need to know if the machine is off in either direction, the alternative hypothesis needs to be that mu is not equal to 20.1. So this will be our first two-tailed test, so that's why this one's important for us. Now let's go ahead with step 2. Step 2 is just to find alpha, so we know that alpha is 0.01. And now we can do step 3. And remember, step 3 is calculate the test statistic, find the critical value using the table, and then draw the normal curve and shade alpha on the normal curve. So I'll go ahead and calculate our test statistic here. That's going to be x bar minus mu divided by s over square root of m. And our test statistic is 1.042. And I'll go ahead and sketch our normal curve. Since this is a two-tailed test, we're going to need 2 critical values, and we will shade both tails. Now remember, alpha is the area in the tails. It's just that we have 2 tails here. So if alpha is 0.01, then each of these tails has an area of 0.005, and each of these tails actually represents alpha over 2. Now you'll go to your t-table, and using degrees of freedom of 10 and an area of 0.005, you'll find a critical value of 3.169. So the left critical value will be negative 3.169, and the right critical value will be positive 3.169. Now we can draw our test statistic onto our normal curve, and that's a very middle of the road 1.042, so that's going to be about here somewhere. And as you can see, our test statistic fell in the non-rejection region. So we would not reject H0, and we would say that there is not sufficient evidence to conclude that the mean weight of the candy bars is different from 20.1.